Okay, so the first law that I want to talk to you guys about is called Dalton's law of partial pressures. To me, in my mind, as we're talking about pressure here, it's kind of the first one, and it kind of makes it's pretty easy, and it kind of makes straightforward sense to me, at least. So let's talk a little bit about it. So as I've been talking so far, in my head at least, I don't know if this is what you guys have been picturing, but I've been kind of only thinking about a sample containing one type of particle of a gas, right? So I've just been talking about a gas, but what if we have multiple gases in a sample? So Dalton's law of partial pressures deals with the fact that we might have multiple kinds of gas in a sample. So thinking about the kinetic molecular theory of gases, we can also apply these ideas to a mixed gas sample. All of the rules still apply here. If we have a mixed sample of gases, it's basically like having individual gases, individual samples of each gas. You might think of them in separate containers, but if we just shove them all into one place there, it's like having like I said, it's like having all of those individual samples. They're just all in the same container or all in one place. So they behave just as if they were hanging out by themselves. They're just in a group, right? Which makes sense because when we think about kinetic molecular theory, it states that gases are not interacting with each other. They're just moving in these straight lines. There's lots of spaces between particles, and that their motion changes with the temperature. So none of that has anything to do with the type of gas or saying that different gases interact differently with each other. So we can just assume that kinetic molecular theory applies separately to all these gases, but we all got them in one spot. That's basically it. So Dalton's law of partial pressures helps us to describe what happens with the pressure and which gas contributes how much to the pressure based upon the mixture of the gas. So, for example, here I put up on your screen the kind of composition of air. So, air is actually made up of 78% nitrogen. In our heads, we kind of think about it as oxygen because that's the most important molecule to us for life. But it's only 21% oxygen. I don't know if you've ever seen it. There are places where you can go and you can breathe in pure oxygen. It's supposed to be good for you. I have no idea, but it's because air is actually really 78% nitrogen. So every time you breathe in, you're breathing in nitrogen, oxygen, argon, carbon dioxide, all of these other things around you. But when you breathe out, what you're doing is you're releasing most of those gases in their original state back in. They're not actually participating in a chemical reaction. It's only the oxygen that's participating in the chemical reaction that we need. So when you breathe in, you're breathing in about 78% nitrogen, and you're breathing back out all of that nitrogen all the time, and argon and all those other gases. So I don't know, I think that's kind of a cool fact that air is made up of all these different kinds of gases. So when we breathe in, we're breathing in lots of different things. We're not only like somehow filtering just the oxygen molecules out of the air. So cool thought. But as we're thinking about this composition of air, what it's really telling us is that, in the way kinetic molecular theory kind of describes the behavior of gases, basically we're saying that, okay, if air is made up of 78% nitrogen, 78% of the pressure that we feel from air is from nitrogen, okay? So whatever proportion of the total mixture that gas makes up, it contributes that much to the pressure, right? If you think about it, each individual gas, we're assuming it behaves like it normally would, so it has its pressure, and we add them all up to get the total pressure of what's in the container. Makes sense to me. I don't know about you guys, but makes sense to me. So, Dalton's law of partial pressures, if I say it in a more plain, straightforward way, is that the total pressure of a sample of a mixture of gases is equal to the sum of the pressure exerted by each gas. So each gas has what we call a partial pressure. So partial pressures are denoted with the P with the letter of the gas below it. So if we have hydrogen, we might say P sub H, oxygen, P sub O, neon, P sub Ne, or something like that. So the idea is the partial pressure is the amount of pressure each individual gas contributes, and P sub TOT, P sub total, is the entire pressure in the container. So what does this look like when we start to actually think about this and think about questions. So again, Dalton's law of partial pressures is that the total pressure of a sample of a mixture of gases is equal to the sum of the pressure exerted by each gas. So again, as I just said, the capital P here is for partial pressure, even though we use capital P to mean regular pressure most of the time too. So partial pressure is the contribution of the individual gas to the total pressure. So P sub A is like the fractional amount of the component times the total pressure. At least that's how the book says it. Kind of clunky. So what this is really saying is it's like the percentage the percentage of the composition that gas takes up. So whatever percentage of the gas is the one you're studying, you use that as a decimal as always. We can only do math with decimals. We can't do math with percents. And then so I'm telling you how to I'm sorry. I threw myself off hardcore. So I'm telling you how to convert. So the part the gas contributes divided by 100. So if it's 78%, you're going to divide 78 by 100 to make it that decimal. So that's kind of the idea here. So a partial pressure is like the fraction that the fraction of the total gas that individual gas takes up. You're going to multiply that fraction by the total pressure to find the individual amount that pressure contributes, or that gas contributes to the total pressure, which we call a partial pressure. So I wanted to mention really quick here, we've got a new unit to learn about pressures. We haven't discussed pressures yet, so we have not met a pressure unit. There are lots of different pressure units out there. So you may have heard of pounds per square inch before, right? So however many pounds are pressing on a square inch is a pound per square inch, okay? So that might be something you're familiar with if you're like filling up tires on your car, your bike, what have you. So PSI is something you may be familiar with. You may have also heard of atmospheres. That's the amount of pressure that you feel from the atmosphere at sea level is 1 atmosphere. So you may see kind of different pressures like that. I think the book also mentions millimeters of mercury, and it also mentions torr. But like I said, there are lots of different ways you can measure pressure. But the way we are going to measure pressure in this class is, of course, with this SI unit. We talked before about SI units. So we're going to bring it back here that the SI unit of pressure that we're going to study in this class is going to be the Pascal. So I'm not going to ask you to convert between different pressure units, and I'm not asking you to memorize how to convert between different pressure units. I just really want you to understand what the Pascal is. A Pascal is the SI unit of pressure. It's abbreviated capital P, lowercase a, so you have to make sure you're using that capitalization correctly. Capital P, lowercase a. And it's equal to the force brought on by 1 Newton per meter. So we're thinking of like, a pound as an amount of pressure, pound per square inch. This is a Newton, if you may have heard that before in your other classes. It's also a measurement of force. So this is saying 1 Newton per meter squared. You don't have to know what that means. I just want to tell you if you know what a Newton is. So that's how a Pascal is technically defined. But as a more qualitative way that we may have experienced Pascals, it's actually 101,325 Pascals. That's what you feel at sea level. So when you're just sitting around and you're at sea level, you will feel 101,325 Pascals of pressure on you, okay? We're pretty close to sea level here. We're not that far off. So this is relatively what we experience in our everyday lives. So let's go ahead. We're going to work through some examples that might be how I would ask these questions for you on an exam or something like that. How might I ask you to apply Dalton's law of partial pressures?
Okay, so we're going to go ahead and do our first example for Dalton's law of partial pressures. So the question is asking, what is the total pressure exerted by a gas with the following partial pressures, okay? So we're going to try to apply Dalton's law of partial pressures here. So remembering that partial pressures are each of the individual contribution of the gases to the total pressure of the gas. So here we have a partial pressure of oxygen that is 159 pascals and a partial pressure of nitrogen that's 593 pascals. So we can write down our equation, which is P total equals P sub O plus P sub N, because these are our two partial pressures. And here we're given P sub O and P sub N, and we are going to be looking for the total pressure. So we're looking for the total pressure, and we've been given P sub O and P sub N. So P total equals 159 pascals plus 593 pascals. And then we can add those together to get what our pressure total is. So our total pressure is going to be that 159 plus 593, so 159 plus 593 is 752 pascals. So our answer here is 752 pascals. You always have to make sure that you have the correct number of significant figures, of course. This one has 1, 2, 3 sig figs, 1, 2, 3 sig figs. My answer has 1, 2, 3. We're good there. And, you know, I can kind of triple check that I've got the right thing going on. Again, because I have partial pressures adding to a total pressure, our answer is going to be 752 pascals for the first one there. So 752 pascals. Okay, so I have another example to work through here over Dalton's law of partial pressures, another kind of exemplary question I might ask. So what I want to know here is, what is the partial pressure exerted by oxygen in a sample of gas with a total pressure of 2,256 pascals and the following known partial pressures? So we're given some of the partial pressures of our mixture, we're given the total pressure, and we're looking for a partial pressure of oxygen here. So let's go ahead and write out our equation and start to fill in the pieces that we're told in our equation. So we have total pressure is 2,256 pascals, and we know these known pressures down here. So our equation, it needs to be the partial pressures of all the gases we're given added together. So the first partial pressure we're told about is oxygen. We want to know the partial pressure of oxygen. Partial pressure of oxygen. We're given the partial pressure of argon, AR. We're given the partial pressure of neon, Ne. And we're given the partial pressure of helium, He. Okay? So, slanted down there, huh? So this is our equation representing the total pressure as being added up, or as the sum of all of the different partial pressures. So let's go ahead and start to fill in some of our known values. So I'll just start from left to right. Do we know the total pressure? Yes, and this time we actually know the total pressure. We're given that it's 2256 pascals. Do we know the partial pressure of oxygen? No, that's what we're looking for, so we're going to leave it as partial pressure oxygen. And then we know the other three partial pressures. They were given here. So the partial pressure of argon is 698 pascals. The partial pressure of neon is 569 pascals. And the partial pressure of helium is 123 pascals. Okay, so that being said, we can now go ahead and solve for our partial pressure of oxygen, since it's the only thing left here. You could do this one of two ways. You could either add all of these up first and then subtract from 2256, or you could subtract them all individually, which is what I tend to do. So I would go ahead and I would say that this is the partial pressure of oxygen equals, remember, to get rid of addition, you just got to subtract from the other side. So 2256 pascals minus 698 pascals minus 569 pascals
minus 123 pascals. So our partial pressure of oxygen is going to be equal to 866 pascals. 866 pascals. Okay? So, this kind of makes sense, right? The way partial pressures work. So, like, if I want to know the partial pressure of one and I'm given all the pressures of the other and the total, it's just what's left over, the pressure that hasn't been accounted for by the other three gases. So all we're saying is the total pressure, take away the pressure from argon, take away the pressure from neon, take away the pressure from helium. Once you've done that, you're with whatever's left, that has to be the pressure from oxygen, because that's the only thing left in that container exerting any pressure. So that makes sense here. So when you're working through these partial pressure problems, you should always make sure that your partial pressures are smaller than the total pressure, right? Because the partial pressures have to add up to be the total pressure. So in any case, the largest number you should have should be the total pressure. So that checks out here. My partial pressure from oxygen is only 866 pascals, whereas the total pressure of the gas is 2,256 pascals. So that makes sense there. One thing I want to point out here too is, of course, I'm keeping my sig figs as well by writing this as 866 pascals. Because, of course, when we're doing significant figures with addition and subtraction, it's all about the number of spaces after the decimal point. Well, none of these have a decimal portion, so so whenever I'm writing my pressures out, when I get my final answer here, my final answer is whatever the whole number portion is. In this case, it's 866 pascals. No decimal points to account for in our significant figures here, and that's the only thing that matters in addition and subtraction. So, checks out here that I have the correct number of significant figures, and so I can very confidently say that my partial pressure of oxygen is going to be 866 pascals. Okay, so I have one last variation of a question I might ask about Dalton's law of partial pressures. This law of all 6 that we're going to learn total is just a little bit, it allows for a little bit more variation in how I'm going to ask the question. So one last example here for Dalton's law, and then we'll move on to some other laws. So this question states, how much pressure does each gas exert if the total pressure of a gas with the following composition is 101,325 pascals, and then it gives percentages of each gas, the percentage that each gas contributes to the total composition of the gas. So, we want to know what is the partial pressure of each of these individual gases. Well, as we may remember, the partial pressure is just this percentage as a decimal times the total pressure. So it's not that complicated. So in this case, we have 78% nitrogen in our mixture. So I would say that this is 78 divided by 100, or 0.78 times 101,325 pascals. Okay? So it doesn't matter whether you use the fraction, it doesn't matter whether you use the decimal, either way is fine. Here I'll use the fraction, later on I'll use some of the decimals. This is 78% of that total pressure is contributing from nitrogen. So 0.78 times 101,325 is 79,033.5 pascals. However, of course, we have to keep this in the correct amount of significant figures. So here are percentages, because they are so deeply ingrained in our problem. We're going to use those for significant figures as well. So our percentages in this case do count for significant figures. So I'm going to go ahead and write my answer with 2 sig figs for nitrogen, because it has 2 sig figs as the lowest number in the problem. So this is going to be 79,000 pascals as my answer. So 79,000 pascals in the end. So if I want to do the same for oxygen, I take 21 divided by 100, which is 0.21, times that original total pressure, which is 101,325 pascals. Oops, forgot my Pascal. And if I multiply that out, I get 0.21 times 101,325. So I get 21,278.25 pascals. However, again, I have to make sure I'm keeping my significant figures. So I'm going to go ahead and write my answer with 2 sig figs because I get 2 sig figs from the percentage from oxygen. So that's going to be 21,000 pascals. All right, let's do argon and carbon dioxide. We're going to keep moving. So if I want to figure out the partial pressure of argon, I'm going to take 0.9 divided by 100, which ends up being 0.009. And then I'm going to multiply that, of course, by my total pressure, which is 101,325, if you have forgotten. And I'm going to go ahead and do that multiplication. And in this case, I get 911.925 pascals. But here I have one significant figure. Of course, that leading zero doesn't count. So I have 1 sig fig. So I'm going to go ahead and write my answer as 900 pascals. Okay? And last but not least, let's go ahead and see how much carbon dioxide contributes as well. So as always, I'm going to take my percentage. I'm going to divide by 100. It can be kind of complicated. You have to remember that even though these are already small decimals, that they are still in percent form. So they still have to be divided by 100, even though they are decimal numbers. It feels kind of gross because what we have is 0.0004. That's 0.04% written as a decimal. You still have to add in those other 2 zeros, even though it kind of already looks like it should be in decimal form. It's not. So 0.004 times that 101,325 pascals. So if I go ahead and I do that multiplication, I end up getting 40.53 pascals. And here, of course, we still have 1 sig fig. The zeros here don't count. So I'm going to go ahead and write my answer as 40 pascals. All right? So that is how you find the partial pressure of individual gases. If you're given a total pressure and you're given their composition, you just have to make sure that you convert all of your percents to decimals, and then you can just multiply that value times the total pressure to get your partial pressure. Pretty easy. So that's Dalton's law of partial pressures. Hope you enjoyed it.